Hi everyone, so nice to be here. So I'm going to talk about limits of WebAssembly as a bridge from Rust to JavaScript and TypeScript. So a little bit about me. I'm Alberto Schiabel, alias Jcomino on GitHub. I'm an open source engineer at Prisma, but I'm also a freelance consultant. I've been mostly working with Node.js and TypeScript since 2015, but I've also tried a few other languages like C++ and Haskell. More recently, I've been really enjoying Rust since 2020, and I'm fond of functional programming. So we already had a great presentation about WebAssembly for games. Let's get a bit more into that. So first of all, WebAssembly is not a language, right? It's just a portable binary format that basically ships its own virtual machine based on stacks. And it allows code written in other languages to be loaded and run in JavaScript environments and any JavaScript runtime. For this talk, I'm going to focus on Node.js. In Node.js, for instance, WASM modules can be imported as if they were other standard JavaScript modules, so it's pretty handy. IBM, for instance, made a benchmark a few years back, and they realized that the same logic written in Rust was, and then converted to be imported as a WASM module in Node.js, was up to 50 times more faster than the same code written in JavaScript for CPU-bound tasks. And it's well supported since Node 8. All right, so we're going to focus on transforming Rust logic and Rust data structures via WASM to import them in JavaScript and in particular in TypeScript. We're going to attempt to serialize data structures of increasing level of complexities, because it's very easy to convert, for instance, numbers via the foreign function interface. It's much harder when you get box structs and things like that. And we're going to go over some wasm-bindgen magic. As a little demo, I don't have a game to show you, like the previous presentation from Francois, but I have a language parser and validator written in Rust. And we're going to see how we can execute that in Node.js. All right, so let's start with serialization of data structures. AST, by the way, stands for abstract syntax tree, used for the parser. So again, scalars. Let's take a simple struct of scalar values like booleans, unsigned integers, characters. Easy to translate via wasm-bindgen. You just need to add the macro on top. And you need to compile that with the same commands as seen before. And we get something that works for TypeScript. Like we get a type definition. We can run JavaScript with that. It's a little bit cumbersome. Like it has some methods that we don't really expect. Basically, wasm-bindgen leaks out some internal details to the type. And that makes it a bit more uncomfortable to use when you need to define a variable of that type. The idiomatic TypeScript will be the one at the bottom, just a record without that free method you see at the top. Moving on, strings. With strings, we already see the first compilation errors. Why is that? Well, we can read the error message here. It tells us that the trait marker copy is not implemented for string. What wasm-bindgen does under the hood is trying to apply the copy trait for all the public fields in the structs that are transpiled via wasm-bindgen. However, you can't really do that with strings, right? Strings in Rust are non-copyable. They are clonable. And since objects that are shared between WASM-assembly and JavaScript, they live in the WebAssembly runtime, JavaScript needs to hold a pointer, and then there's auto magic, like JavaScript needs to ask for the properties supported by the object. There's auto back and forth, and wasm-bindgen cannot create the logic for us in this case. So we can do that manually. First of all, we need to drop the public field, and we can implement what's called a getter, right? We have that ID property. Now let's expose an ID method. We just clone the string, and we notice that there's the getter property in the wasm-bindgen macro. And similarly, we can do the same for the setter. This is a bit it's a bit a long code to write, right? So there's this getter with clone attribute that does the same for us. And we get a type output that still has that free method from before that leaks out of the internal details. But OK, it's usable. Let's move on. Lifetime. A lot of Rust data structures will likely have lifetime definitions, right? Well, you can't really share them to JavaScript directly. You will need to hide them somehow or transform them somehow. So what we see here, Rust tells us, well, you know, you're just returning a string, a reference to a string. It's a top-level function, so you need to add a lifetime parameter. OK, Rust, let's do that. But let's put static. But if I do that, then the wasm-bindgen check will kick in, and it will tell us that it's currently not safe, not sound, sorry, to use the lifetimes in Rust wasm. In fact, there is the issue for that. OK, then let's create a struct instead, and we put the lifetime definition on the struct rather than on a function. But again, similar type of error. Let's hide the lifetime description in a wrapper struct. Even though the lifetime definition is static, right? We get this error. The trait bound into wasm ABI is not satisfied. What is this? Tells us that it's not implemented for FT static, and yada, yada, yada. Well, first of all, it's pronounced wasm ABI, not wasabi, like I did the first time. So let's look into that. This is from the wasm-bindgen source code. So basically, there's this into wasm ABI that implements what describe. It has this nice ABI type, and it's a trait for anything that can be directly serialized, passed through WebAssembly via the foreign function interface, using the extern-C signature, basically. And wasm-bindgen uses this to convert arguments and then even return types. In that case, the return wasm ABI trait is used. And we've seen that this inherits from the wasm describe trait. And this is pretty cool. Like the original creator from wasm-bindgen had this idea of a descriptor that basically creates a program to describe the type definitions of Rust structures so that they could be used by JavaScript and then TypeScript. And all the logic of that program is actually compile time only, so then it's stripped out of the WebAssembly artifact. And there's a link to that. I'm going to share the slides with you, so if you want to follow along. All right, so let's move on to some more complex data structures. Vectors. Everybody needs vectors, right? You can't always have known-size arrays. Well, what we have here is a structure, vecstruct params. It holds an ID with a vector of foo. And foo is just a struct that holds a scalar value, bar with an U32. We notice that both structs have the wasm-bindgen tag, right? So the macro is kicking in. But we have this foo JS object is not satisfied. And the trait JS object is not implemented for foo. So what this tells us, really, is that we can't have a vector. We can serialize a vector of a generic type. A similar case, instead, is that a simpler case, sorry, is just using a vector of scalars, in which case we get a serialization. It works, it compiles. You can use it on TypeScript. It's not really a standard vector for JavaScript land. It's a uint32 array, which is very similar to the shared buffers you will use with web workers. So it's basically a byte array. And the idiomatic TypeScript for that will be just ID of number and then the square brackets for indicating an array. And again, there's an open issue. It's been open since 2018. So it's a pretty old problem. So moving on, we want to create a parser. And the easiest way is just defining abstract syntax tree. Maybe you want to have a set of accepted values, right? A closed set of accepted values. For instance, I'm defining here a provider, a database provider. It might be Postgres, MySQL, SQLite. And this translates one-to-one with TypeScript just by applying the wasm-bindgen macro. Fair enough. However, the idiomatic TypeScript definition will just be using disjunctions of literals, string literals, or again, just a closed set of strings. But it's usable. We can do that. It's not a limitation, right? Let's move on. Rust has this fantastic feature of abstract data types, or algebraic data types, sorry, or enums, right? So we have a URL, constructor, static, and env. They both hold a string. This defines URL value that you can either read from your environment variables or from just a string static definition. Ideally, we would like to map it to discriminated unions in TypeScript. So it's we have a tag that just tells us the name of the constructor, basically, and then a value that holds the actual value that we want to represent. And this is a pretty handy representation because we can then pattern match on JavaScript land depending on the tag property, so depending on the type of URL that we want to represent in this case. However, this is not supported. We see this error here. Only C-style enums, which are the ones we saw before, are allowed with wasm-bindgen. So basically, over the foreign function interface, we can only serialize enums if they are compatible with integers, just like they are in C. And there are a few discussions going over in the issue highlighted above. There was even a PR that was open a few years back. Unfortunately, the original author couldn't proceed. If you really want to help in the community, jumping on these issues would be great. So, can we do better, right? We see that wasm-bindgen is a pretty useful tool. I love it. But when it comes to, for instance, type safety or expressiveness, sharing expressful data structures from Rust to JavaScript, it has some limitations. And like the Romans said, all the roads lead to Serde. Serde is the de facto tool for serializing things, right? So there's this nice little library, which is officially supported by the Rust WASM project, which is called Rust wasm-bindgen, which is a native integration of Rust and WASM. They claim it's faster than the JSON representation, like the JSON serialization. It only requires a few macro attributes, which are standard for Serde, so just serialize, deserialize on all the data types that you need to return from the Rust land to JavaScript land. And of course, if you have dependencies, so dependent types, you need to apply the same definition on top of them also. And the cool thing is, those ADT enums that we have just seen before, we couldn't transpile via wasm-bindgen are supported, and we can even customize them as we want to get idiomatic TypeScript as an output. We just need to use the derive feature from Serde. However, we cannot return directly the type definitions from WebAssembly to TypeScript. What happens is, while we can share the data, like we can return data, that's not a problem. We need to serialize that to a string first. Why is that? Because the return wasm-API trait automatic implementation doesn't kick in with complex data structures. So we're still back where we were. What if, like this is basically TypeScript that really wants to use WebAssembly, right? But can't do that right now. Can't do that, man. What if there was a magic tool that allowed us to get WebAssembly with types, right? And that one, like, little backstory. When I applied for this talk, I had no clue that this tool existed. So this talk was mainly about limitations. Now I can finally provide you with a solution. This tool is called TSify. It's a very recent library, like only 13 stars on GitHub. Please add some more. It's an idiomatic TypeScript definition generator for Rust and WebAssembly. It supports all the nice features that we struggled with before. So it supports ADT enums, box structs from the standard library, so you can share hash maps, you can share vectors, vectors of vectors. You can just go play tricky with that. It supports alias types. It builds on top of Serde, wasm-bindgen, so the same library we've seen before. It uses a lot of macros, unsafe code, magic. It needs to even parse the macro definitions via the Darling library. And it implements that from wasm-bindgen trait we saw before, the wasabi one, for all the standard library data types. And here's an example of that. Like, first of all, we just need 3 imports, basically. The standard, the serialized and serialized from Serde, the tsify top level module, and then the wasm-bindgen prelude, which is like the standard library for wasm-bindgen. We see that tsify accepts some feature flags. We'll get into that later. Basically, they will allow you to customize the way you serialize your data. And here's a little example. We want to create a discriminated union of a URL in this case, the same example as before. We start with the standard derivation macro. So serialize, deserialize, those are from Serde, and then tsify. We apply the tsify macro. We see we have into wasm-bindgen, from wasm-bindgen. That's just a little trick to implement those traits we've seen before under the hood. And this is just a customization we can apply via Serde. So this is a feature native of Serde to get those discrimination data types output back. So we got those underscore tag and value for static and URLs. And this is just the whole code. So finally, we have idiomatic TypeScript definitions from our Rust, structs, and enums. And that's great. So moving on, we can just show you a little bit of differences between a little bit of things you need to be aware of if you need to compile code both for Rust and WebAssembly, and then we can move on to the demo. So by default, if you need to compile a library in Rust, the default type crate is lib or rlib. WebAssembly is a bit special in that, right? It requires a system library. So the official suggestion by the Rust WASM team is to just support the cd-lib target, linkage target. You can actually compile your Rust code targeting both cd-lib and rlib, which is what we're going to do. This is an example schema to parse. I'm going to spell it out just for the people in the back that might not see the screen. So we have an example of the Prisma schema language. I'm not sure how many are familiar with Prisma. It's mostly a product used in the TypeScript land, but I guess half of that code is written in Rust. So we're pretty involved in that. And it allows you to define database collections that then you can query with our tool. So we define a database in this case. Provider is Postgres. We could use MySQL, we could use SQL Server. We define a URL. We want to read that from the database URL. And then we can define another shadow database URL, which basically we use for schema migrations. And we define it as a static string, right? So this will be the type definition that we expect as an output for TypeScript. So we see discriminated unions for the provider, which is idiomatic. We see the URL, again, spelled out as an abstract algebraic data type. I always mistake that. We see an object for the data source DB top-level object. And then there's this schema AST, which just represents the collection of all the possible data sources you might have in a schema. And how does this translate into WebAssembly? How can we return some complex data structure from Rust and then use it later in JavaScript? So what we have here, we just have the top-level definitions we saw before, Serde and wasm-bindgen. We don't see tsify here because that's hidden in another crate, that schema parser crate. This will be the definition of the function defined in the schema parser crate. You will see that in the repository. In that crate, we only toggle WebAssembly, so all those WebAssembly macros, depending on a feature flag. So you don't need to have longer compile times in your main code if you don't need to use WebAssembly as a target all the time. Like you can just opt in later. Here we see this is the function that we expose from Rust to JavaScript. Parse schema wasm, it just accepts an input string. We see it's able to return a result. So this translates into just a value on JavaScript land or an error, like an expected error that you need to try catch, basically. We see that we have a complex return value from that parser schema. It returns that schema AST. Schema AST has the TSC5 macro, so it's a complex data structure. It's the equivalent of the TypeScript definition we've seen before, written in Rust. And it has vectors under the hood, it has enums, etc. The only thing here we see is that we need to manually convert the error type that I'm getting from a string to a JS error. This is I can do that via serd.json. And it's only used for errors anyways. This will be the definition. So demo time. You will see that the repository, it's the top listed in my GitHub account, so github.com, jcomino. Hopefully you can find that in the schedule link from the EuroRust, because it's pretty hard to spell. And EuroRust-2022 is the repository name. So I need to, yeah. So the first thing I will show you is how we parse the schema. The schema is this one, by the way. So, yeah, it's this one. So we see the data source, provider, your URL, and she database URL, so the same as before. And we try to parse that from Rust side. So this is just a Rust CLI application. OK, we parsed that successfully. And this is just the debug print of the data structures we had used in Rust. So we see that top level schema ST, there's an array of data sources, the enums used as ADTs. We see that we have an option type because the shared database URL is optional, so that it's wrapped in a sum constructor. OK, we might validate that. Because I also inserted some validation rules. For instance, yeah, sorry. Validate. For instance, I wrote the code such that it panics. Just a plan. This means that we cannot support environment variables right now. This is an expected panic. Applications can have it, right? We see a message explicitly telling us what's the problem. It's all right, we can fix that. So we just take this, take out this env definition, right? We save it. Now we have just static URLs, so we no longer expect a panic. So the schema is parsed correctly, but we have a validation error. We see that the URLs for the Postgres provider can only start via the Postgres protocol, right? So we need to change that. Just let's copy this, paste it in, and let's try again. And everything parses and validates successfully. Now this is easy done in Rust. We didn't serialize any data structure. We are, however, using an artifact that we wanted to use on wasm-assembly as well. So we have had to compile for both platforms. Now let's use that from Node.js land. First, let's try via just schema parsing. OK, and we see that's parsed successfully. Let me. So we see a similar output. We have a type value here. We see a data source is a DB type. It has a Postgres provider. The shared database is null. Unfortunately, in JavaScript, we have nulls. So we can always improve that. Now let's see what happens when we have errors and panics, because this gets a bit tricky. So first of all, let's validate that. We're not using the same schema now. We're using predefined schemas. Here we have an error. It tells us that the provider, CockroachDB, is not supported. OK, fine. We see an error. We see explicit messages. How about panics? What do you expect will happen with panics? OK, this is a bit hard to parse. We see a few hexadecimal values. We see a runtime error unreachable. But that's not the panic message that we saw before, right? With WebAssembly, we lose all information about panic messages. And that's just only one of the limitations. Of course, you already know that we lose all input-output information. If you have any print line, any warning, you lose that because WebAssembly doesn't support input-output. WASI does. You also cannot catch a panic. In Rust, you call it technically unwind panics. You can no longer do that in WebAssembly. And even in the Rust WASM demos they show online, they tell you, well, technically you could be able to show the message, the original message for your panics by writing these 100 lines of code, right? But you cannot really capture that. You can only print that to the standard console.error method provided by JavaScript. So you will need to call a JavaScript method, and you will lose access to the actual error. You can only print that. So that's a limitation. All right, moving on. So to wrap this up, WebAssembly is very useful. It's here to stay. Like, I think the first major platform that used WebAssembly was Figma back in 2016, 17 at least. And they have just been acquired for a lot of money. So I think they were on the right way. wasm-bindgen is a great tool, but we have seen it has some limitations. It limits your expressiveness for the structures. Unfortunately, some problems have been known for a while and haven't been solved yet. So if you're into open source contribution, please give a hand. Standard wasm-bindgen overcomes most of the limitations we've seen for wasm-bindgen, but it's still not enough for TypeScript users. And I would assume that in most complex Node.js projects, I would assume most of them are written in TypeScript, because once you try types, you never really go back. So TypeScript is pretty important. It's also 10 years old now. It's pretty stable. TSify is a promising new tool that basically provides the best developer experience I had so far for this type of interchanging between data structures between WebAssembly, Rust and WebAssembly, and TypeScript. However, it might be hard to introduce that in your company. Why is that? Well, first of all, it relies on a lot of macros. There's a lot of magic under the hood. Your other colleagues might not be comfortable with having such a magic tool as a dependency. You might increase your compilation times. It's also not that well tested, not well documented yet, but we have seen it's a really recent tool. So hopefully it will become more mature. I would also imagine at some point they will merge some of the features that TSify provides into the wasm-bindgen repository directory. I will love that. So just to wrap this up, WebAssembly is really underrated. If you haven't had the chance yet, try it. All right, that's all from me. Thanks. You see a sample code and a lot more demos actually in the GitHub link, jcomino/EuroRust-2022.